So as Francois previously nicely introduced, I'm going to focus on our activity in photonic neural networks. And here, previously we started with nonlinear dynamics in delay systems, but as the field matures, we started to move away from nonlinear delay dynamics to more spatial temporal systems for some technical aspects. But here, to match better to the GDR, I will focus on our recent activity about integration in 3D, because we use a technique which might be relevant also for the topics which are discussed in, maybe in later meetings. So just a very simple, quick overview. So neural networks are conceptually rather simple. They consist of thousands or millions of nonlinear nodes, which are connected via linear weights into a network. So abstracted like this, they are very simple. They approximate an input to output nonlinear function, which in the end is what you would consider a computation. You send some data in, you get some data out. And by using examples, usually one adjusts the network topology until, for example, the results are the ones you desire. And then if the network was trained properly, it can generalize, which I will show you later. But then they are very complex because they essentially harbor millions of parameters, all these connection weights. And typically these nonlinear nodes, they also have a constant bias offset. And what is done is then using these example data, the topology of this network is optimized using statistical physics techniques of optimization, just as if you do a nonlinear curve fitting. You define some target function, for example, the error. And then these parameters are basically examined against their gradient on this error function, and then step by step this network topology is optimized until the final result comes out. So what are they useful for? Just recently there has been a big hype about, for example, that these networks can predict the folding, for example, of non-trivial protein structures, which is a more biophysics, biochemistry kind of relevance. But what makes them really special is that they can be solved on problems where you don't really have an algorithmic approach to solving the computations. So to algorithmically predict how these protein structures fold is highly non-trivial, and it has actually been identified as one of the applications for quantum computing. So what you do in neural networks is you use example data and you trust that the system, when it's trained correctly, can generalize. So what this means here is, for example, shown at the bottom, you can, for example, use paintings of the classical masters, like typical styles which were developed in Van Gogh, for example, in Belgium. You use sceneries where the painter has, for example, taken inspiration and then has done its interpretation of that scenery. You can train a neural network to understand the functional connection of the style represented by, for example, a particular painter. And then you train the network, but you can then generate new images by present new scenery to it. And because the network has approximated essentially the style of that painter, it can then transfer it into these new images. So that is the very important property of neural networks, that they can generalize. If you provide a sufficient example data, they should be able to approximate a certain functional relationships to a certain degree, of course, and then they can show this for other data belonging to the same class. The problem with neural networks is exactly this kind of strength, which basically rests within this high-dimensional connectivity. So this is taken inspiration, as you can see by the name, as from neuroscience. And here's a sketch of Ramon y Cajal from the previous century, where you see the soma. So what you could say is, in first principle, the nonlinear body of a neuron. By now we know that's too simplified. And then here you see the connectivity branch of such a biological neuron cell. And if you just want to realize this in artificial hardware, you can see the challenge we are facing. So this is called the interconnect, and this might be the curse, particularly for electronics, and a blessing at the same time, maybe for photonics. So in electronics, switching an electronic wire just by capacity and charge has an energy penalty associated to it. And the problem is the scaling of this energy penalty. The capacity of such neighboring wires scales first, of course, with their length, with the surface area. But then if you look at the distance between those, it depends on the logarithm between the width and the distance of such a wire. So in other words, if you reduce the size of electronic integration, like it's always done right now in these different technology nodes where you go until 12 nanometer, which is commercially exploited right now, essentially all you can hope for is a linear scale improvement. And this is essentially what leads to the performance limitation in today's integrated electronics because of the dynamical switching energy associated with switching electronic wires. Photonics provides a really attractive escape route. The wires have no capacity, no induction, and by now photonics have very low propagation losses. But of course, we have much larger feature sizes just because of the de Broglie wavelength of an electron is of a very different scale than the wavelength of the optical wave functions. So this is not so new within the field. That's been discussed to do optical neural networks actually since the 80s, where this work was pioneered by Dimitri Psaltis. In this decade, however, what takes off more and more is the integration efforts of such neural networks. And here now we find another limitation. So imagine you want to integrate such a connectivity matrix in a photonic circuit. So that would be, for example, a mesh of Mach-Zehnder integrators, which can implement a unitary, random or arbitrary unitary matrix. This is here shown in hardware. The problem is that the number of connections scales quadratic with the number of input and outputs, so the size of the network, and that fundamentally results into quadratic scaling of the required infrastructure in 2D. So if we go into the brain, autonomy of the brain, on the most simple scale, what the brain leverages is actually a 2D, 3D approach. Neurons are mostly located on the surface of its aggregations here, but the connections are done in 3D. And if you compare this just from a more geometric point of view, if you connect a one column vector to a row vector, then you need this kind of area in terms of to implement the connectivity matrix. So the area scales quadratically with the number of neurons you want to implement. If you do the same thing in 3D, you can define your input not as a vector, but as an array. And then you just make layers. In each layer, you can, for example, connect one of the input nodes to all the other output nodes. And with this, the footprint of this circuit scales linearly. So we have used 3D direct laser writing in order to implement such structures. In 3D direct laser writing, what you use is a photoresist, which is a liquid monomer. You use a femtosecond laser to tightly focus the light within this volume. And then essentially by high energy pulses, what you do is a transformation of the monomers into chains of polymers. And these polymers are then developed and form into a solid structure, while as the liquid photoresists we can easily wash away. So this is additive manufacturing. And with this, we can, of course, make very complex structures in 3D. The important part here is that the polymer is transparent at optical wavelengths, and due to the two-photon process of the polymerization, we can beat the upper resolution limits. So that means we can go to really high resolution 3D printed structures. This we explored first with rather, let's say, simple waveguides. We simply wrote 3D polymer guiding structures, and since the high refractive index contrast, we get very strong confinement for optical propagation along these 3D polymers. So if you would think in the context of neural networks, this here would be the position of one of these nonlinear nodes, for example, neurons, and then the waveguides in these directions, including all these branches, basically implements this 3D connectivity structures. And we've explored here different degrees of connectivity, where here every input connects to 9 outputs, here every input connects to 81. And here we have basically realized a complex network connecting more than 200 input channels to, I think, over 500 output channels. And here you see the power of the 3D integration. You could never implement such a thing in the 2D, considering the feature size, because it would essentially take the size of an entire desktop. We implemented more complex 3D connectivity structures, which are more relevant for neural networks. So, for example, convolutional filters. I don't want to spend too much time on this. The important is that here on the volume of a couple of micrometers, we can essentially implement 9 half filters, 9 convolution half filters, which would work completely in parallel and are completely passive. So besides optical propagation losses, you would have no energy penalty when you want to implement this for the network connections. So now let me focus a bit more on the relevant topic for this GDR. 3D printed waveguides are actually not so straightforward as you would imagine from the 2D fabrication, where you use very high quality lithography. Here we have additive structures, and we have additive construction of the final geometry using the 3D voxels. And what you can see, what results from that is, if you want to, for example, write one of these 1 to 9 splitters, then if you zoom in, you would get these agglomerations of voxels, and therefore you get an undulation of the surface, so surface roughness. And in particular for periodic propagation of optical wavelengths, this is not so far away from the periodicity which we encounter in our structures, so we expect actually some interaction with this. So this is where we started recently some simulation activity with the master intern student from the Karlsruhe Institute of Technology, who will join my group now starting February. So based on a 3D CAD program, we approximate or we model the 3D volumetric structure of our waveguides. And you can see here for a few examples, essentially what we do is we stack these 3D voxels where they overlap. They are basically Boolean combined in an OR operation. And then we have the really arrogated surface of these waveguides, and then using finite element simulations through COMSOL, we essentially now started the simulation of these structures. And that is the current starting point. And one could imagine, for example, going further in this direction and actually investigating optical propagation into of 3D printed structures, which use this to really design newer structures and new types of matter. And here I selected 2 interesting examples. This was actually demonstrated and realized already in 2006 by, let's say, one of the pioneers within the field of 3D 2-photon polymerization printing, Martin Wegener in Karlsruhe. And they printed some really interesting structures, so quasi-crystals, and then they investigated the scattering spectrum from these structures. Other work, for example, done in the last months of last year, so this field really takes a lot of momentum at the moment, is, for example, to 3D print photonic crystal waveguides, where you can get really a high, highly unusual propagating modes, for example, this annular mode here, etc. Or you can print photonic crystal polarizing beam splitter. They essentially use the band gaps and directionality of the propagating solutions in order to implement polarization beam splitting. So I think the kind of freeform aspect of the 3D printing really gives a lot of room to play around and to make really investigations into more novel photonics or in general waveguiding structures. And this is a bit also the transition to the presentation which will follow now by Xavi, where we continue to explore waveguides which don't simply consist of a polymer core and air surrounding, but more like core-cladding structures. And with this, I'd like to thank you for your attention. When you have questions, just ask me, or we continue with Xavi. I don't know.